Hey class, welcome back to Electromagnetics. So we're continuing our look at Maxwell's equations and how we use them with circuit analysis, maybe kind of backtracking on what we've looked at before. So previously we looked at static fields, but now we're going to look at very low frequency behavior via quasi-statics. And so that's kind of what quasi-static implies, that it's not really a static field theoretically, but it's not time varying enough to where it really kicks into some of the higher order issues in Maxwell's equations. First, a quick historical background. So this individual, University of Caen, I guess, in Normandy, worked at École Militaire. Here's a picture of this individual. This is Pierre Laplace, which you've heard of Laplace transform, and we looked at Laplace's equation. Some of the notable things, he's referred to as the French Newton, where as Newton was in England. This is a guy who's doing many of the same things and the same magnitude of work in France. He advanced many of the works of Newton on celestial mechanics. He solved the great Jupiter-Saturn inequality problem. So if you look at astronomy, there was an issue with the calculations that they were trying to do with that, and he figured that out. He came very close to predicting black holes. He dealt a lot with massive stars and light and some of the calculations involved with that. He developed the first analytic theory of probabilities, and then of course finally what most of us know him for is he developed the Laplace transforms. So he was an extraordinary individual. While he was somewhat a man of faith, he did struggle with things, and on the next slide you'll see the famous quote or issue that he dealt with, which many people refer to as either Laplace's demon or Laplace's Superman. And as a result of all his work that he did, he made this statement. He said, "We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed. If this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the moments of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present before its eyes." And so while he struggled with the idea of God or there being an all-powerful being, from his own study he realized that with the complexity and the beauty and the precision of the way the universe was formed and how it worked and interacted, it really spoke to or pointed to there must be some superior being with superior knowledge that set all this in motion. It couldn't have just happened by mere chance. So again, we're continuing in part 6. We're going to look at low frequency behavior via quasi-statics, kind of the next step up from static fields. So in the previous lecture, we considered fields that didn't vary with time at all, and then we applied Maxwell's equations to these situations. We now want to extend this analysis to low varying fields, that is, if the frequency is low enough. The analysis derived in the previous chapter is still valid. It's still a valid approximation of the response of the system and the components, and it does have some usefulness. So the quasi-static approach or assumptions are typically valid in the cases where the structure length in the direction of propagation is very small compared to the wavelength corresponding to the frequency of the source in the dielectric. So if you get to the case to where your device is 40, 50, 60 cycles in length, then these don't apply. But if it's a half a cycle, or a quarter of a cycle in length of the wavelength of your frequency, then these would probably hold. So looking at the capacitance as we did before, or the whole circuit, where we could even have current flow, we're going to define an electric field in this case in terms of the voltage source V0, so we'll call this E0, and again it's the divergence of this, or the gradient, excuse me, of this, and so that's V0 over D cosine omega t. So again, we're assuming that this omega is a pretty low frequency. So this results in an associated magnetic field where we can take this first derivative with respect to z, and we're saying 1 because this is going to be, remember when we did the solution by successive solutions equations where we kept circling everything back in and substituting back in. Remember, there were 2 methods. There was either the wave equation or successive solutions. We were looking at the successive solution approach here, and so that's why we're saying this is the first approximation of the magnetic field. And so when being that we had an expression for the electric field, we can associate that to the displacement current field by the permittivity. So we plug that in and take the derivative, and then, the integral, and we come up with this. And so this is our first approximation. And so this is not a complete solution, as we recall from the successive solution lectures a few lectures back. But we're going to stop here with this first order approximation, and you'll see that it does have it is reliant on the frequency here. So we can now work from here to obtain the current from the source, so this current density. So we have this IG, we'll see the IG here, it's what's coming from our source, and it's just going to be the width times our magnetic field, first order approximation that is, and so when we plug those values in, you can see we come up with that it's the capacitance times the derivative of the voltage, the time derivative of the voltage. And so in this case, we can just say that I is equal to j omega c. So we're using that phasor notation as we did back in that when we worked with those successive solution steps. So we can also look at the power flow. So the power in is going to be the width times the depth times the electric field times the magnetic field. And so you see the notations here. So the 0 is, this is what we define the electric field. So that's the 0th order, 0 order approximation there, and then that led to the first order approximation of the magnetic field because we had that one integral step in between. And so when we plug in the values for these, which we have values for them, we come up with this resulting equation here. And so what this turns out to be is the time derivative of the power stored in the capacitance. So with this new application, we can now, as previously, derive an expression for the magnetic field as follows. So we could say that the first order magnetic field is equal to this source current, which we defined before, over the width times this cosine omega t, the driving function of our source. So this results then in an associated electric field. So now we're looking at the electric field. This is the first order approximation. We can relate the flux density field to the magnetic field by the permeability. So we do that here. And then we have this first order approximation once we plug all that in and take the integral. So again, though this is not a complete solution, we stop here for the first order approximation in terms of the frequency. So we can now work from here to obtain the voltage then across our source. So here we're saying that the voltage is going to equal to d times the first order approximation of the E field. And when we plug the values from the previous slides in for these and gather like terms, we see that that we found the definition of inductance and so forth. And so this is basically equal to the inductance times the time derivative of the current. So hopefully these equations that I'm ending on, these should be familiar to you from your circuit analysis classes, because these are what you're taught in circuit analysis. And so finally, this can give us an expression here for our voltage, again using the phasor analysis that we used before. So we can also look at power in this sense, in terms of what's the input power. So we have our width and our depth times our electric and magnetic fields. And when we plug all this in, we can see that it's going to be the time derivative of 1/2 the inductance times the current squared. So as before, the electric field then, this is when we're having the resistance. We have the V0 over d cosine omega t. So in this case, it leads to the definition of this current density, which we just multiply times the conductivity of the material in the middle. And so we can now also derive an expression for our current density in the magnetic field. So our current density, again, we have just multiplied by the conductivity, and then our magnetic field from Maxwell's equations results here. So what does this look like? So in this case, where we do have this current flow between the two parallel plates, we can see that our electric field is constant all the way across. We see that our magnetic field, the first order magnetic field, drops off a little lower than because of the intrinsic impedance. It'll be a little lower than the E field, and it drops off if we move along the plates here until it's 0 at the end. So the interesting thing is here, we can look at the results of, if we take our first order approximation of E and then our first order approximations from the magnetic field, you can see that you will get some variances as you take these solutions through, but usually the first order approximation's good enough. So we can now also derive an expression for our source current. And so our source current should be equal to the width times our magnetic field. And when we plug in the values for this, for each of the scenarios, so this would be due to resistance, this would be due to capacitance, this would be due to inductance. This can now be calculated as an input admittance. So if we take the current over the voltage and plug those values in, we can make some reasonable approximations and reduce this down. We finally land on what we are used to seeing from circuit analysis, j omega c plus 1 over the resistance times j omega the inductance. And so just kind of taking some quick steps. I'm not really concerned that you understand or are super familiar with how we got from one place to the other. I mean, it's great if you want to go back and work through that. But the biggest thing is, one, to demonstrate to you that we can use Maxwell's equations and work through and come up with the equations that you learned in circuit analysis, so that when you get into situations, depending on what direction you go in your career, if you get down to small enough issues, or you start having some extraneous issues with your circuit design, it would help you to have some understanding of where these equations came from and how you can even dig down a little further to maybe take a look under the hood and see what's really going on.